Hello, I'm Rick Watanabe from Mitsubishi Electric. Today, I'll present enhancing shoulder haptics on the hand by viewpoint shift in VR. Let me briefly present the abstract of this work. We address the issue that weight moderation shoulder haptics has been limited for full body motion. To tackle this issue, we propose scaling not only the virtual hand but also the virtual viewpoint. As a result, viewpoint scaling moderates perceived weight more than hand-only scaling in full-body tasks. Next, I'll present the introduction with recent advances in VR technology, where task training is expected to enable efficient skill transfer across sectors such as industry and logistics. However, to make skill transfer more effective, visual guidance alone is not sufficient. Posture and haptic feedback are also important. Haptics has been studied extensively, and one notable approach is shoulder haptics. Shoulder haptics intentionally induce visual proprioceptive discrepancies by modulating visual stimuli to evoke haptic sensations. For example, if the virtual hand appears to move more slowly than the real hand, users perceive the object as heavier. If it appears to move faster, they perceive it as lighter. Because shoulder haptics relies only on visual stimuli, it is low cost and scalable. Here, we want you to know that shoulder haptics in prior works in hand-centric and mostly seated. However, when VR task training is deployed in industry and construction, we often need to simulate full-body tasks, for example, installing or replacing or positioning utility poles or manhole covers. If these tasks are simulated without a full-body posture or even without weight feedback, the gap between the simulation and the real work can increase injury risk. As mentioned, the above shoulder haptics depend only on hand, so it is limited for full-body tasks. Therefore, this motivated us to expand shoulder haptics to provide full-body weight sensations. While that prior work about vection showed that changes in viewpoint can moderate perceived body motion and influence self-motion perception. In the driving simulator, it enhances perceived acceleration. Building on two insights, scaling hand position moderates the perceived weight, and viewpoint changes moderate perceived body motion. We hypothesized that scaling the viewpoint can enhance hand-induced perceived weight. Next, I'll explain the proposed method. As shown in these equations, we scale both the virtual hand and the viewpoint by applying a gain K to the actual vertical displacement. We use two gains. K8 is the virtual hand gain. Kv is the virtual viewpoint gain. When the gain K equals 1, their hand and virtual motions align. When K is greater than 1, the virtual position enlarges and appears to move faster. When K is less than 1, the virtual position shrinks and appears to move more slowly. The video illustrates differences in the viewpoint gain. Please focus on the contrast between the middle and the right clips. Visually, as the virtual displacement increases, the viewpoint rises faster, making the object motions appear slower relative to the eye. Next, I'll present the experiment. In the preliminary study, we identified the perceptual thresholds for the hand gain and the viewpoint gain. These thresholds determine the parameter levels used in the main experiment. In comparison 1, participants compared a lift with the hand and viewpoint gain set to 1 to a lift where only the hand gain varied from 1 down to 0 in steps of 0.2. In comparison 2, participants compared a lift with the hand and viewpoint gain set to 1 to a lift where only the viewpoint gain varied. After each pair, participants reported difference weight for the hand-only comparison, body movement for the viewpoint-only comparison. We analyze the result by plotting detection rates and fitting a sigmoid function. Detection thresholds defined at the 0.5 probability criterion, as is common in psychophysics, were estimated at 0.633 for the hand gain and 0.637 for the viewpoint gain. Both the hand and viewpoint gains showed thresholds about 0.4 below the baseline of 1. Therefore, to provide a clearly perceptible contrast in the main study, we choose values twice that offset, 0.2 below the baseline, along with the baseline 1, and the symmetric higher values of 1.8 as the experimental parameters. In the main study, we examined how gains of hand and viewpoint affect perceived weight. Moreover, since prior work has shown that large mismatches between the actual and the virtual reduce presence, we likewise investigated presence. Participants compared a lift with the hand and viewpoint gain set to 1 to a lift with the gain from one of the 9 conditions in the table. After lifting tasks, participants rated the control conditions in 10 Likert scale. Participants gave higher ratings as the object felt heavier and higher ratings as their sense of presence increased. First, I'll present the result for perceived weight using an ART ANOVA. We found a significant main effect of both hand scaling and viewpoint scaling on perceived weight, while the interaction was not significant. The figure plots the mean perceived weight for each condition. Consistent with prior work, lower hand scaling made the object feel heavier, whereas hand scaling made it feel lighter. By contrast, lower viewpoint scaling made the object feel lighter, while higher viewpoint scaling made it feel heavier. The result supports the hypothesis that scaling viewpoint can moderate hand-induced perceived weight. When the object feels heavier, either hand scaling is lower or viewpoint scaling is higher. Conversely, when the object feels lighter, either hand scaling is higher or viewpoint scaling is lower. This suggests the hand velocity relative to the viewpoint drives weight perception. Smaller feels heavier, larger feels lighter. Postural stability may also matter. Under heavier impressions, the body rises fast, like lifting mainly with the hands, reducing whole body support. Under lighter impressions, the body stays steadier while the hands move more freely, like the whole body helping the lift. Actually, last night, we shot these videos, and you can see if we will lift heavy object. We try to lift it with whole body, but when lifting a light object, we can do it with the hand. This empirical knowledge could have influenced the result in the experiment. In short, perceived weight is moderated by relative velocity and postural stability. Next, I'll present the presence results. An ART ANOVA reveals significant main effect of hand scaling and viewpoint scaling, as well as a significant interaction. The figure presents the mean presence ratings for each condition. Although we achieved our goal of enhancing perceived weight by scaling by the viewpoint, we also noticed a trade-off for presence. When we pushed for lightness with hand gain equals 1.8, increasing viewpoint gain to 1.8 could restore presence, but this reduced the lightness effect. In other words, boosting presence here comes at the cost of perceived lightness. By contrast, when hand gain equals 0.2 or 1, viewpoint scaling had little effect on presence. Presence remained relatively stable, even when the object felt heavier. To summarize this discussion, exaggerated lightness reduced presence more than exaggerated heaviness. To close, 3 implications for shared haptics design. Hand motion scaling creates weight illusions without disrupting presence. Viewpoint manipulation is a useful scan channel. It shifts perceived weight by a visual body mismatch. Coordinating hand and viewpoint enables nuanced control of the perceived weight while preserving presence. These results extend shoot haptics to full body motion and can boost learning in VR task training. Next, we'll test complex object geometries, multi-joint and collaborative tasks, and personalized gains. We'll also study for body effort beyond hand lift, like standing with a loaded backpack. This is summary of our contributions. Thank you for your attention.
Yeah, so we have time for some questions. Are there any questions from the audience? Yeah, then I think I'll initiate with my question. I think you already put in the future work that you're gonna apply this to other motions. So in the study, I see the mostly, I mean, its study is based on the lift motion, right? So what type of other hand and body related motion can this be applied to?
Do you mean that in the future work?
Yeah.
So stand motion.
Yeah, other than just the lifting motion, is there any other type of the motions in VR that we can apply this to that you are foreseeing?
So stand motion is in the VR task training is important. So we focus on viewpoint and hand for full body tasks.
Okay, got it. Yeah. Are there any questions? Okay, then let's give applause to the presenter and we'll move on to the next presentation.
So thank you very much. I'd like to start by sharing some examples. When grasping objects in daily life, we observe that people usually apply different hand poses to different objects. For example, sometimes the thumb is opposite to the index finger, especially when the objects are small and light, as shown here. And sometimes the thumb is opposite to the middle finger. And sometimes the thumb is opposite to the ring finger, especially when the objects are heavier and larger. Actually, I have some more examples I just have with me. So this is a little cup, a little souvenir I got last night when I was drinking. So when I'm holding this, I will use my index finger and the middle finger. It's weird to hold it otherwise. So this is our habit and observation. Also, I've got my iPad mini. My hand is large enough to hold it with one hand. So when I'm holding this, usually I will use my these fingers instead of the index finger because it's too large for the index finger to hold it. So this is a simple observation. That means people decide how to grasp objects based on the object's properties. So it's what's happening in reality. However, in virtual reality, we face the challenge of providing immersive haptic feedback. So is it possible then to simulate the object properties reversely by changing the user's poses of grasping? So here I present our work, thumb shift, modulating perceived object properties through dynamic thumb repositioning. I am Jian from the University of Melbourne, and the co-authors of the paper were Gavin Beckham from University of Exeter, Wafa Johar from University of Melbourne, and Gerald Knipp from University of Queensland. So immersive haptic feedback remains a grand challenge of virtual reality. Passive haptic feedbacks leverage physical objects in the user's environment to provide feedback. And the visual haptic illusion allows for a certain mismatch between the virtual and the physical object the users are interacting with. So for example, with the approaches such as the precise grasping, one physical object can actually represent a range of different virtual objects in VR. And active haptics use mechanical devices to change the physical properties directly. For example, the X-rings can expand and contract to change its size directly. There has also been technique combining illusion in active head devices to render different properties. In this case, the fingers are repositioned by the device while the size of the device doesn't change. This motion provides a perception of size changing. So this approach actually comes from an observation of how different objects are grasped in daily life. When grasping objects of different sizes, both the contact surface areas and the finger poses are changed. Also, the fingers collaborate to contribute forces in grasp. Studies have shown that the force distributions of fingers change when grasping different objects. Here we see a change of force on each finger when the object size changes. So again, our hypothesis is it possible to inversely trigger the illusion of holding objects with different properties by altering the force distribution? So we propose and explore dynamically repositioning the user's fingers and thus the force distribution to change the size and weight perception. We call this technique dynamic digit positioning. To study the effect of this technique, we propose thumb shifting to move the thumb. We designed the Haptics study device to render subtle shifts in the finger collaboration. The thumb is located on the thumb pad and the other four fingers on the other side. And the thumb can be rotated and moved on the device as shown here. Now it's moved just slightly. So we utilized one motor and a pair of gear and gear rack to realize the movement and a servo for the rotation. We set up the environment with a set of motion capture system and the thumb shift device, along with a set of MetaQuest 3 for rendering the VR scenes. We estimated the size and weight perception in our study when using this device. For size perception, we use a two alternative forced choice task where the participants compare the size of the physical objects they are holding in their hand and the virtual one they are looking at, and they need to answer is the virtual one smaller or larger. And for the weight perception, we applied a magnitude estimation. The participants report a number and it's recorded in the virtual scene, and it represents how heavy the participants think the device is. Following standard practices in magnitude estimation in psychometric work, we applied a series of data processing after gathering the results. So we first studied if and how does changing the grasp configuration impact size and weight perception. We have two conditions for the first study: the static configurations. That means the configuration doesn't change in each session of answering all these questions until all the questions were answered. For this configuration, then it changed to another configuration. That means another pose of holding the device. We have 3 different positions for the thumb and 3 different orientations for the thumb. So this is a simple example of how it's done. At first, the participants answer a series of 2FC questions, and she holds the device, answer virtual smaller or virtual larger. And this is a demo for the magnitude estimation. She reported a number, and it's recorded in the virtual scene. And when she answered all the questions, the configuration will change, the thumb moved, and at the same time, the participants were asked to perform a stroop task to be distracted from this change of configuration. And a new series of questions were asked. So we calculated the proportion of the 2FC task answers and feed them into a sigmoid function. At the 50% point, the participants generally believe that's the size they perceived when they're holding that device. And people don't notice the difference between the other 2 points, the 25% and 75% perceptual thresholds. After putting the results of these configurations into one bar chart, we found that there is actually not large change on size perception in the static condition. And also from the magnitude estimation, there's also no significant change in weight perception in this condition. And we have also the dynamic condition. That means the thumb pad will move in different sequences between these 3 locations. And every time after the movement, the participants are asked to answer the question. After answering the question, it will move again. So it's movement, answer, repeatedly. We have 6 different moving sequences, moving down and up between these 3 points and 3 directions again. So similarly, there didn't seem to be a large difference in size perception in the dynamic condition either. However, we did find that the thumb moving sequences showed significant influence on the weight perception, taking the mean value of the estimation as 100%. The weight perception results were shown here. The largest comparison appears between IOMO and MOIO. That means the thumb is moving between the index finger level and the middle finger level. This proves that dynamically repositioning the thumb can alter weight perception effectively by up to around 19%. So the takeaways from study 1 is, first, the size perception isn't changed in the digit positioning. However, the weight perception is changed in dynamic movement of thumb by up to around 19%, but not when static grasping it. So we then further explore if other factors also influence the weight perception here. We examine how the mass center position and the size-weight illusion will influence the weight perception, because these two were proved to be influencing the weight perception in many previous studies. We designed 2 different mass center positions for the second study. One is higher, one is lower, with an additional weight load. And after all the estimation for the mass centers, we removed the weight load, and we presented 3 different virtual sizes from 5.5 centimeter to 6.5 centimeter. So these are 2 conditions we estimated in study 2. From the estimation results, the effect of moving sequence on the weight perception is still significant. In addition, the position of the mass center largely impacts the weight perceptions too. On general, as you can see here, the participants perceive it to be heavier when the mass center is higher in the blue bars and lighter when the mass center is lower in the orange bars. So together, if we compare the largest comparison, the weight perception can be changed by up to 56%. The virtual size, however, does not have a significant impact, indicating the size-weight illusion also isn't working effectively here. So takeaways for study 2 are: the weight perception is further influenced by the mass center position, making the weight perception changed by about 56%. And the size-weight illusion didn't impact the perception, possibly due to the virtual size range being too small, only from 5.5 centimeter to 6.5 centimeter. That's not a very large difference in the virtual size, so the size-weight illusion may not be working here. The summary of these studies is the size perception doesn't change in digit positioning, and the weight perception is only changed when the thumb moves instead of in different static grasping poses. And changing the mass center also impacts the weight perception. And the implications for VR haptics from our study is, first of all, in previous studies, weight perception was a challenging VR haptic field because the approaches are either costly, bulky, or not as effective as expected, or limited to certain movement. However, in our study, we proved that it can be effectively changed by dynamic digit positioning to simulate weight change. For example, when the users hold a virtual cup and pouring water inside, then simply move the thumb, it can change the weight perception and simulate this sense. And the dynamic digit positioning can be easily realized by adding a single motor to any existing controller just to move the thumb. And if you have one additional motor, it's even better because you can move the mass center inside with another motor, and it will largely enhance the ability to alter the weight perception here. So for further details, we invite you to explore our paper on my website by scanning this QR code. Thank you very much.
Yep, thanks for the presentation. Are there any questions from the audience? Yeah.
Thank you for the interesting talk. I'm Yusuke Uchitoko. I understand your device changed the position of the thumb when you're grasping something, but when your device change the position of the thumb, the participants may feel the external force from the device. So my question is there any possibility that the participants judge the object property based on force rather than positional cue?
Yes. In our theory, we changed the force distribution by changing the position of moving the thumb. So we actually, in this session, we added force sensors on each finger pad to see how the finger force contributing to the device changed. And it actually can explain part of the results that the fingers are contributing force in lifting this device in different ways when it moves. So the weight perception can be changed. So yes, I think that's one of the explanation of this phenomenon.
Thank you.
Thank you.
Yeah, question. Yeah.
Yes.
Thank you very much for that talk.
Thank you.
I'm wondering about like future studies you might run because you're not finding the difference in size, which I think is it's partly due to the range you're looking at. So that was a good insight. Have you thought about something that I think is really interesting about VR is you can change the material properties of the visual object, right? So when people have sort of cognitive biases about which things are going to be heavier. And so you might be able to push around your effect if you change the materials. Have you thought about that?
Yes. I think this is a very interesting field to explore because I mentioned the size weight illusion in study 2. If there is so if you knew this concept before, the size weight illusion means when the virtual size doesn't really match with the physical size you hold in your hand, there is an illusion feeling the device is actually heavier or lighter. And one of the explanation of this phenomenon is that people expect it to be heavier when it looks large and expect it to be, but it doesn't, it actually is not that heavy. So I think it can also apply to the appearance of the material. If it looks heavy, but it doesn't really feel heavy, the participants may, on contrast, feel is actually lighter. So I do think the visual appearance of it influences a lot. So I would call this more like visual haptic illusion that happens only in VR and XR field, rather than like when we're blind, not looking at anything. So yes, I think it's a very interesting topic.
Yeah. Due to time, we'll move on to the next presentation. Yeah. Thanks again for the presentation.
Thank you
Yeah.
very much.
Thanks for the introduction. Hello, everyone. Today I'll present our work, design and evaluation of pseudo-haptic techniques for simulating surface thickness in VR. I'm Yutaro Hiro, and this research is a collaboration with my co-authors on the list. In this talk, I'll introduce how we design pseudo-haptic cues to simulate the feeling of stickiness, a tactile quality that has not been fully explored in virtual experience. In everyday life, we often interact with sticky materials, from glue, clay, and tape to syrup, or even our own skin after applying lotion. These interactions are characterized by delayed detachment and resistance while separating surfaces. However, in VR, simulating stickness while attaching and detaching interaction remains challenging. Existing method utilizes various physical actuators such as electro-adhesion, ultrasound, liquid, or friction-based devices. These systems are effective, but have a trade-off between the complexity of the device and quality of the stickness presentation. And they typically only simulate planar or horizontal friction stickness. To address this, we propose a pseudo-haptic approach for simulating sticky attachment and detachment. This video shows the implementation of our techniques. To simulate the virtual stickness, we combine several pseudo-haptic cues. First, visual physical discrepancy, also known as motion gain, is a conventional pseudo-haptic technique. It introduces the movement of the virtual hand, it reduces the movement of the virtual hand relative to the controller creating a feeling of resistance. Second, surface deformation. Visually stretches the virtual surface depending on how much the hand is pulled, just like a sticky material stretching before it breaks. Third, vibration feedback provides a continuous low-frequency vibration while the hand is attached and a sharp pulse when it detaches, enhancing the sensation of adhesion and release. Finally, the breaking height trigger defines the exact moment when the surface visually and physically separates, keeping the timing consistent across all cues. Together, these cues generate a unified illusion of stickiness in VR. When we look at it this way, we can see that creating pseudo stickiness actually involves many interrelated parameters. Each contributes differently to the overall experience. However, it is not obvious how each of these pseudo-haptic cues or their combinations actually affect the perception of stickiness. Therefore, rather than simply proposing a novel pseudo-stickiness technique, we aim to establish design guidelines for parameter tuning through psychophysical experiment. Specifically, we conducted 3 experiments to answer the following research questions. The first experiment, how does each cue or combination affect perceived intensity of stickiness? Second experiment, does the range of presentable stickiness differ between 1 cue and 2 cues? I mean, here the presentable stickiness means the maximum and the minimum levels of the stickiness. And the third experiment, does the resolution of perceivable stickiness differ between single and multi-cue conditions? All right, so let's start with the first experiment. In the first experiment, we examine how each pseudo-haptic cue and their combinations contribute to the perception of virtual stickiness. We tested 10 conditions by combining motion gain, deformation, and vibration. The gain of 1 means no special effect. That is, the virtual hand completely follows the controller. On the other hand, the gain of 0 indicates that the virtual hand does not move until the controller reaches the breaking height. The bottom right shows the visual deformation of the surface. Participants touched and lifted their virtual hand from a sticky plane in VR, and after each trial, they rated their experience on a 7-point Likert scale with the question of, I felt like I touched a sticky surface, from strongly disagree to strongly agree. Each condition was repeated 6 times, resulting in 60 trials per participant. This is the result of the stickiness question. Obviously, participants did not feel any stickiness without any cues. Also, the condition having all effects induces the stickiest perception. Also, the condition, an interesting thing is that combining even 2 cues enhances the pseudo-sticky sensation than the single cue. As another result, the single vibration has the weakest effect on the sensation. Here, we can say that first, each pseudo-haptic cues contribute to pseudo-sticky perception and has different effectiveness. And combining pseudo-haptic cue can have a stronger effect than single cue in general. So to summarize the first experiment, both the gain and the deformation cues work well, and overall, the more cues we added, the stickier it felt. So let's move on to the second experiment. The second experiment examined whether multiple cues could expand the acceptable range of visual physical discrepancy. That is, how far the virtual hand can deviate from the real hand before the illusion breaks. Here, we compared 2 conditions. The first one is stuck condition, where the motion gain is set to 0. In this case, the virtual hand remains fixed to the surface until the participant lifts it above the breaking height. This represents the single cue condition, since only motion gain is used. The second one is the moving condition, where the motion gain is 0.15 and the visual surface deformation cue is added. This corresponds to the multiple cue condition, combining both visual surface and proprioceptive cues. By comparing these two conditions, we examine how the addition of multiple cues affect the perception of pseudostickiness. In this experiment, two thresholds of the visual physical discrepancies were investigated following the staircase method. One is the low threshold, where participants first sensed stickiness, and the other is the high threshold, where participants start to feel that the interaction is unrealistic. The figures show the average of the thresholds. The top figure indicates the high, and the bottom indicates the low threshold. Also, left condition is the stuck, and the right condition is the moving condition. As shown in the figure, the low threshold, which represents, again, the minimum discrepancy required to feel stickiness, was significantly smaller in the moving condition than in the stuck condition. This means that when multiple cues were presented together, participants started to perceive stickiness earlier or with smaller visual offsets. However, when we look at the overall range, defined as the difference between the high and low thresholds, we found no significant difference between the two conditions. In other words, the addition of the multiple cues enhanced the sensitivity to the onset of stickiness, but it did not extend the total range of acceptable discrepancy. To summarize the second experiment showed no big change in range, but multiple cue made people notice stickiness sooner. All right, so this is the final experiment. The third experiment investigated perceptual resolution, how finely users can distinguish different levels of stickiness. Using the method of constant stimuli, participants compared surfaces with different breaking heights and indicated which felt stickier. On the right, you can see the psychometric curves plotted for all participants. The stuck condition is drawn in blue and the moving condition in red. The slope of this curve is clearly steeper in the moving condition, indicating that participants could more precisely discriminate differences in stickiness when multiple cues were presented. Quantitatively, the just noticeable difference here, described JMD, meaning the minimum visual physical discrepancy required per participant to notice a difference in stickiness, decreased from 3.4 centimeters in the single cue condition to 1.9 centimeters in the multiple cue condition. This corresponds to a 44% improvement in perceptual resolution. In short, adding surface deformation alongside motion gain enabled participants to detect subtler variations in visual thickness. Okay, so let me wrap up with a quick summary of the three experiments. In the first experiment, we found that combining multiple cues made the surface feel stickier. In other words, multiple cue stimuli enhanced the perceived intensity of stickiness. In the second experiment, adding more cues helped participants notice stickiness earlier, reducing the detection threshold. Although it didn't really change the total range where the illusion worked. And in the third experiment, the combination of cues sharpened perception, improving the resolution by 44%, meaning participants could tell finer differences in stickiness level. Altogether, these results show that multiple cue pseudo-haptics not only make the illusion stronger, but also make it more precise. We believe this contributes to a deeper understanding of pseudo-haptics and often have a possibility for creating more tactile and immersive VR experience in the future. Thanks for listening, and I'm happy to take any questions. Thank you.
Yeah, thanks for the talk. Are there any questions from the audience? Yeah.
Thank you for your presentation. It's quite interesting. But I noticed that in many of your experiments, the virtual hand avatar includes the forearm, but in the most commercial headset, we have only the hand as the metaphor. So I noticed that the forearm, the movement of the forearm can also provide some cue that how stick that the surface is. So I'd like to know your thoughts on the role of the forearm that plays in your experiments. Thank you.
Thanks for the really nice comment. So yeah, I agree with that. The forearm movement would affect the sense of stickiness, I guess. But in our experiment, we are not intendedly designing the movement of the forearm. So that means like the forearm is just follow the motion of the hand. I mean, they are not moved. I mean, they are just stuck on the hand movement. But actually, the previous work designed wisely the different motion of the hand and forearm, and they separate the motion of the hand and forearm, and then it shows that the user less notice the discrepancy between the physical and the virtual movement difference. So that means like we can utilize more bigger discrepancies without noticing the difference between the virtual and physical motion. So I think we can utilize that knowledge to our stickiness technique too. Thank you.
Yeah. Are there any more questions? So yeah, I have just one quick question. So I think based on the experience with the studies, so I think I saw that the vibration has very little effect on the inducing the stickiness. So have you ever considered also other type of the physical modality like the squeezing or something else, maybe inducing more? Just wonder. Yeah.
So you mean like using the vibration to the squeezing effect or squeezing the tactile?
I mean the squeezing as a physical squeezing, like
physical
other type of
squeezing.
modality.
That's interesting. I
Yeah.
mean, we are not tested yet, but yeah, there are several papers that try to use a shear force on the skin to present the sticky perception. So I believe that that kind of haptic stimuli would improve the sense of stickiness.
Got it. Yeah. Yeah. So thanks for the presentation. Yeah.
Thank you.
Okay, hello everyone. My name is Shu Xiliao, and I'm from Purdue University. Today I will introduce our paper, The Effects of Realism on Hand Redirection in Immersive Environments. And hand redirection is a very powerful technique in VR. The VR application can basically reposition the user hand without letting the user notice about that. So why would you want to do that? One reason is for haptic feedback. Redirection can allow a VR applications to use the same physical objects to provide the haptic feedback for multiple virtual objects. For example, in this paper, there is a single physical cube here to impersonate the 3 virtual cube in the virtual environments. And redirection also works in conjunction with the ETHD of robots, basically, that helps to move the physical object towards the user with safety and with lower latency. And in another example, redirection can bring virtual objects within the user's reach. Instead of requiring users to hyperextend their arms or hands to reach the virtual objects, hand redirection enables the interaction in a more natural and a comfortable way. So thanks to the hand redirection provides such powerful capability for users in virtual reality, would it be nice to extend this into mixed reality? So here we provide a very simple video to show the concept. When the redirection is off, the user can see she's touching the same targets on the table. So when the redirection is on, can we make the user see she's touching the different targets in the mixed reality headset, while in the physical world, she's actually touching the same targets multiple times? So there is 2 questions based on this. One question is, can it be done from a technical standpoint? First, we need to find the hand in the live frame. then segment it out from that frame. Then we need to reconstruct the 3D hand and render it to a new position. And finally, we need to fill in the holes left at the old hand position. So these all are challenging tasks, especially if the background has a very complex geometry and its dynamic is moving. So the second fundamental question is, assuming we can solve these technical problems, is hand redirection in mixed reality useful? Essentially, can we hope to trick the user into not noticing that their hand is actually at a different location? So our guiding research question is, what are the detection thresholds for hand redirection in MR compared to VR? We formulated two competing hypotheses. The first hypothesis is that the MR threshold are less than the VR thresholds because the user is very familiar with seeing their own hands as they move it. So if you detect there's even tiny little manipulation during the task. Or maybe that's the hypothesis too. The MR threshold are greater than the VR because seeing their actual hand makes users less likely to suspect that its position has been redirected. So we argue that the second question should be answered first. In other words, let's first see whether the hand redirection in MR is useful before we tackle this perfect implementation. So what we did is to put together a hand redirection pipeline that relies on several simplifying assumptions, just to give ourselves a chance to investigate the question too. Here is our hand redirection. It leverages a flat background of a uniform color, and it renders just the hand as the 2D sprites. So this allows us to conduct a user study to compare the hand redirection detection thresholds between the VR and the MR. In fact, we have 4 conditions with all possible combinations between VR, MR hands, and scene. The first one is the pure VR, VR hand and VR scene. The hand here is a generic 3D model. Another condition is all MR, MR hand and MR scene. The hand here is rendered from a video frame of the user's hand. An MR hand VR scene and VR hand MR scene. The participant had to touch the virtual green dog on the table. For each child, there are 2 touches, one with redirection and the other without. The participant is then asked to indicate in which touch their hand did not move as expected. And there are 17 possible redirection offsets for each of the 2 physical target A and B here, ranging from -12 to 12 centimeters. And offsets are either horizontal and vertically. So here is the VR hand, VR scene condition. We need at least 2 physical targets for user not to memorize the positions for no redirection. And here is the MR hand and MR scene condition. The users can see their physical surroundings and their actual hands during the task. And we notice that in the virtual first-person view, the virtual target position is changed, while in the corresponding physical position, the user keep touching the same points. So here are the remaining 2 hybrid combinations between the VR and MR. Let's take a quick look at them. So here is a brief summary of our most important results. The graph shows the psychometric sigmoid function fitted into our data. And there's one graph for each physical location in A and B, and also the offset direction horizontally and vertically, X and Y. And x-axis is the magnitude of the offsets in the centimeter, and y-axis is the rate of the correct answer. The detection threshold is measured at the interception with the 17.5% correct answer rate. And here are the 32 threshold for the 4 graphs. And in the second row, LM represent the left and the near, which means the negative direction of the offsets. And right and far represents R and F represent the right and far, which is the positive offset direction. And furthermore, we also calculated the overall threshold for each location A and B, and each redirection, direction X and Y, and also all the locations and all the direction. And as you can see, the MR hand shows a higher detection threshold than the VR hand. And for example, at the physical position A, here the MR hand exhibits an average of detection threshold 8.23, which is approximately 1 centimeter higher than that of the VR hand, 7.05 centimeter. And a similar trend is observed not only in the MR scene, but also in the VR scene. And here is the violin plots of the answer correctness rates for the 4 conditions. As you can see, the MR hand yields lower values than the VR hand for both scenes. And that means the participants were not able to detect the redirection as easily when they saw their own hand. And however, there's only one significant difference for the MR scene, but not for the VR scene, between the MR and the VR hands. So let's move on to the key findings based on the results. One key takeaway is that for our experiments, when participants saw their own hand, the detection threshold is lower for both the VR and the MR scene. We also found that the MR scene yields a similar detection threshold compared to the VR scene, suggesting that the hand redirection can be applicable in MR environments and not just in the VR environments. And interestingly, in our customized user questionnaires, participants reported a similar perceived detectability across the conditions. And these subjective results contrast with the objective finding. Finally, the SSQ total score remains well below the commonly accepted VR discomfort threshold. And all of these findings indicate that the hand redirection can be feasibly extended to mixed reality setting, opening the door for the future studies in MR-based hand redirection. And thank you. I'm ready for the questions.
Nice talk. And is there any question from the audience? Yeah. So I have one quick question. So when you render this in the mixed reality scene, so I see that currently it is shown on the table with less background, but does it work robustly even in the very cluttered scene itself?
Sorry, can you repeat your
So in the if the background is very cluttered, like many objects behind the hand, does it render like as smooth as possible, like with a real-time support?
Yeah, we tried that before, but actually it's currently very difficult to render a perfect hand, segment it out, and reconstruct the hands perfectly to let the users ignore that effect. So basically we just use the pure color backgrounds to represent these complicated background environments to let us just evaluate whether there is an effect in mixed reality that has this higher detection threshold. We currently just don't focus on the very specific implementation of the background, for example, the segmentation, something like that. But in the future work, once the computer vision techniques become more and more magical, and then we can apply that into the mixed reality hand redirection technique.
Got it.
Does that answer your question?
Yeah.
Thank you.
Any more question? So yeah, that concludes this session. So thanks for all the presenters today.
Thank you.